Hi guys, my name is Samuel Abuaje and corresponding author for this paper is Dr. Lujin Chai. My academic advisor is Dr. Suzy P. And today I'm presenting runtime adaptive transformer acceleration with configurable PE-Mac depth for mixed embedded dimensions on resource constrained FPGAs. The outline for today's presentation is target device selection, attention computations that handles embedded dimension depth, attention computation pipelines, problem formulation. Is it possible to do reduced embedded dimension? Problem statement, our proposed method, integration of our proposed method, and its effects. In target device selection, we use a small FPGA because for multitasking tasks, multiple designs is supposed to exist in a single bit stream on a bigger FPGA. So if it can be realized on a small FPGA, it can be integrated into a single bit stream with other designs on a bigger FPGA. So it reduces reconfiguration overhead. We don't have to reconfigure the board all the time. So that's why we use a small FPGA. And these are the attention steps that handle embedded dimension. So projections handle embedded dimension, QK handles embedded dimension, softmax does not, SV does, layer normalization and nonlinear activation also does. So attention computation pipelines that has been designed on FPGAs on different target devices as this VIDA uses the same board that we are using, talks about column by column computations, fetch the next column while the first column is running, process it column by column because we are using a small FPGA. Heat talks about different quantizations and using more bits for shallow layers, for large layers and small bits for shallow layers. HPTA, there is HPTA design on a big FPGA also, and it presents like ping pong buffering as an idea. SWAT also uses a big FPGA, but it also presents using like data flow logic to handle masking, not applying the masking, using that data flow logic to handle the masking for the shifted windows. And ELSA is algorithm level, but it explores sparsity in the data. And SAAD is kind of similar to what we are doing. That I give alterable data path to the systolic array that it can decide not to add bias or it can add bias, things like that. And that is from SAAD. So the problem formulation uh, is that reduced embedded dimension. Is it possible? So when we are doing the dot product and we wanted to reduce embedded dimension for the projection, for the QKV projections only, then we are reducing the dimension for the input shape. Let's look at the flattened input shape. Flattened input shape is 50625 by D reduced. Now we have reduced the dimension for the input shape. So instead of 180, let's say we've reduced it to like 96. Then the weight shape is also reduced at the first dimension so that it matches when you do the dot product. Then by D, so when that is done, when that dot product is done, the output becomes 50625 by D. So the output shape dimension is unchanged. It gets the full dimension is in the output shape. The output shape is not D reduced. So if we did it for projections only, we don't have to recover the dimension for the output shape. But if we did it for an entire attention stage, then we see how the output shape becomes 50625 by D reduced. So that has to be recovered. And is it recoverable? And yes, it can be recovered by just doing the dot product of the reduced dimension output shape with a weight shape of D reduced by D. So the output shape is recovered. The output shape now for the next stage output shape has become 50625 by D instead of 50625 by D reduced. So the dimension has been recovered at the next stage. So it is recoverable. So it makes it possible to do mixed embedded dimension computations. And this work does not look at accuracy losses that comes with running reduced embedded dimension. We only talk about making the pipeline adaptive to mixed embedded dimension, so that if you reduce the embedded dimension and you run the pipeline, you get the throughput gain. It doesn't run at the same speed as you didn't reduce the embedded dimension. That's what this work looks like. So the problem statement: none of the existing on FPGA work supports dynamic adaptation to mixed embedded dimensions. They are all designed for fixed embedded dimensions, and it results in underutilization when reduced embedded dimension is issued. So when a reduced embedded dimension is issued, it still computes with the same compute depth, even though the workload is now lower. It has been issued for a reduced workload, but it still computes for that compute depth. So it runs on needed depth cycles for reduced workload. So pipeline must be made adaptive for reduced embedded dimension. Proposed method is make it adaptive. We introduce runtime variable called the PEMAC depth to the pipeline. Pipeline now runs for the PEMAC depth between 1 to the max, and windows can be introduced faster at low D stage or low embedded dimension stage, because II is reduced at that stage, and window latency is also reduced at that stage because embedded dimension has been reduced at that stage. And these are not possible if the pipeline is designed for fixed embedded dimension. If it's designed for fixed embedded dimension, the window latency and the II and the window latency will remain the same, it won't change. So runtime depth variable integration, how it is integrated, how we integrate it is the top function receives PEMAC depth value at the output port. PEMAC depth value is given to the, we expose a port called PEMAC depth. So the top function receives PEMAC depth value. Then that value must go to a helper function which clips it between 1 and 180. If the value given it is less than 1, it clips it to 1. If the value is more than 180, it clips it to 180. And if it's in between, then it runs PEMAC depth value. So once the helper function knows the value to run, then it sends it to another variable called the active PEMAC depth. So active PEMAC depth is the one that the top function calls the compute engines with. So the top function calls the compute engines with active PEMAC depth. After active PEMAC depth has been known to it, after it has gone through the helper function and it knows, the system knows the value for active PEMAC depth, then the compute engine call with active PEMAC depth can now run with active PEMAC depth. So window latency is effect. After we've designed it, we've incorporated this helper function into the pipeline design, and we run it for full embedded dimension and look at the window latency for using that pipeline with our proposed method to run a full embedded dimension. That has the window latency become more because now we added like this extra helper function, and the value, the PEMAC, if we are running it for full embedded dimension, that means we are setting the PEMAC depth value to 180, which is the full embedded dimension value. So after it's gone through the helper function, does it result in window latency increase for full embedded dimension? And the answer is no, it didn't change. The window latency remained the same. So, and II also did not change. II also remained the same, and power consumption was also not affected. That means the integration of this small addition to the pipeline did not result in window latency increase and II increase for full embedded dimension computations. And now it can also, the same pipeline can be used to run reduced embedded dimension and full embedded dimension computation. Latency is the same. So how it translated to throughput gain for reduced embedded dimension is we present the ImageNet module, which is what is used in the VIDA paper. So VIDA speed 8.71, adding lightweight softmax paper that is also referenced in our paper. The lightweight softmax integration with VIDA, adding that to it results in the speed from 8.71 to 9.2 frames per second. Now the VIDA plus lightweight softmax, which are all referenced, we reference lightweight softmax integration from another paper, which is a journal, and VIDA is also another paper. So VIDA plus lightweight softmax with full embedded dimension of 180 is 9.2 frames per second, and with reduced embedded dimension for one stage resulted in a window latency of 439,220 and an II of 53,821. And when we plug that into the model, C reduced and II reduced, that is at the stage that we reduce the embedded dimension for. So we plug that in there, it resulted in a frames per second of 9.5 frames per second. So it translates to an increase in frames per second because the T total has been reduced, because the II and the window latencies has been reduced. And if the pipeline design was for fixed embedded dimension, not for embedded dimension that is adaptive to different embedded dimension values, but it actually has a max. It must have that max. So it has a max, but we can now run it for reduced embedded dimension and see that throughput gain. So that is how the throughput gain that is seen when we integrate runtime depth variable into it. So that is it for today's presentation. Thank you so much.